So the last thing I'd like to talk about is not necessarily like solving problems, but the role of open problems within mathematics. When we talked about the axiomatic method, and behind it we would have this whole idea of if I want to build up a system of new knowledge, right? And so we want to go ahead and get through things like the idea of knowledge is just really just simply stuff that is true, right? Whether it's normally within a system, we're building up, this is true, and we go through different properties. Again, at the very, very bottom of all of this are the undefined terms, and then our axioms or postulates, which mean the same thing, which is, so we have statements that we accept to be true, we have things that we cannot define, but we know that they exist, and then we go ahead and build upwards from this. And so we use reasoning. And when we go through here, we're trying to find new things, right? And so the idea of what we call a conjecture, it's just something that we think, but we don't know. That could be true. And so there's an idea as we go through things, and it's like, you know what, this might be true, I don't know. But on the other hand, if we actually do prove it, which is you use logic and reasoning and rules of inference and actually show that whatever you're talking about is actually a tautology, right? So if you actually do prove it, it's a new piece of knowledge, right? And so it moves on to, we can actually rename it. And, we could go through this renaming, and simple terms are things like, okay, it's a fact, right? Normally, if we would go to this, instead of calling it a fact, if it's important enough, we might call it a lemma. If it's a fact that is used to show other things that are more important, we would call it a lemma. If it's really important, we might call it a theorem. And if it's an obvious result of a theorem, we would call it a corollary. But really, in the end, we're just building up a bunch of new truths, right? And so we go up, and we have different terms for it. But how we develop these new pieces of truth from, we define objects that are new, we show things that are true rather than this accepted bottom, but we're moving up, and we're moving from conjectures into facts and lemmas and theorems and corollaries, however you want to call it, but it's just this collection of truths. These tautologies, they're a collection of tautologies that we keep building up and building up. And if they're tied together, we might call it, well, okay, this is Euclidean geometry, and this is number theory, and we go through these little buckets of knowledge, and we'll do number theory in this class. We'll do naive set theory in this class. So this whole process of showing new tautologies is building up things that we know. The role of open problems, right? And a lot of times when we talk about, what's an open problem, really what we're talking about is rather things that are interesting and they haven't been shown, but it's an interesting conjecture. It's like, I really do believe a variant or this particular thing is a tautology, and it makes you want to work things out. We could imagine the concept, for example, if I want to prove the square root of 3 is irrational, before that, I have to prove the fact, right, that if n squared has a factor of 3, then n has a factor of 3, right? So this particular statement is showing this particular fact. This is needed to prove the square root of 3 is irrational. So I would have to do this first. So we could go through this, and because it's used later and it's used in that proof, we might call this a lemma because it's used. But really, when we look at this whole kind of knowledge thing, right? If I start out here at the bottom, I have to get through, what's at this point? Well, this is that whole n squared has a factor of 3 implies n has a factor of 3. To be able to get above it, which is the square root of 3, is irrational, right? To be able to get from where am I at? I'm down here. I have this much knowledge. I want to get up here. Well, the first thing I have to do is I'm going to have to break through. I'm going to have some facts that are necessary to prove this bigger thing. But the moment I've done that, I've increased my knowledge. And so what's interesting about open problems are this whole effect that you can sit there and say, in the same way, when I want to build up knowledge overall, similarly, we could sit there and say, here is where we're at, right? This is all possible knowledge, right? It's like we have these unknowns, and this is what we have so far, right? This is known so far. And what happens with an open problem is that usually it's kind of a jump, right? We have this open problem here. And the idea is how do I get here, right? Do I have to build up some more facts to show one at a time, like first this and this and this, and then I can finally get to my open problem? Is it going to need an entire, class and big giant chunk before I can even get to this open problem? So that's the nice thing about open problems. It's like looking down the road at this incredible problem way up ahead, and it's like I'm going to have to go on this journey to get there. And lots of open problems exist right now, and this is how mathematics is developed. We sit there and we jump from things that we know, and then we build up some pieces and get another part. There's actually a few pieces of things that we assume to be true. It's like they're sitting here, and I've not proved it, but we're going to go ahead and move on if it has. And say, knowing the fact that if this is ever broken, right, everything that I built on top of it falls down in a particular way. And so the idea of open problems is to draw us through, these systems and to work it out. And some interesting ones to look at. Some interesting ones we have is like the book talks about Fermat's last theorem, which has currently been proven. And, a lot of the interesting ones are things that are simply stated. Like Fermat's last theorem was simply that if I want to solve x to the n plus y to the n equals z to the n has no integer solutions if n is equal to 3 or 4 or 5, etc. And so, for example, if n was equal to 2, right, we have x squared plus y squared equals z squared. Well, this forms Pythagorean triples, right, where things like 3 squared plus 4 squared equals 5 squared. And so that's a Pythagorean triple. So if we had n equal to 1, x plus y plus z, equals z, is an obvious, there's an infinite number of solutions. There's an infinite number of solutions of the squares. And there was a book that was written, and Fermat was reading it. And books at the time were published where you would have this, and then we would have the printing, and you had all this lot of white space. And so he was reading about Pythagorean triples. And here in the margin of his book, he simply wrote, if the power was 3 or more, there are no integer solutions, which is a rather amazing statement, because for n equal 1, there's obviously an infinite number of solutions, like 3 plus 4 is 7. For n equal 2, there's an infinite number of Pythagorean triples, and you can write ways to generate essentially the pattern in all of them. But on the other hand, he said that if n was equal to 3, like x cubed plus y cubed equals z cubed, he said no integers would ever solve this. And if it's 4, no integers would ever make this equal, which is a pretty interesting statement. And then he wrote, along with that, it'll have no solutions. And I thought of a wonderful proof, but it's too big for the margin of my paper, and so he didn't write it down. And after he died, his son published that particular, his notes, and people read that, and they spent centuries trying to find, because you look at this and it's like, yeah, I think he's right. And they worked and worked and worked and worked, and mathematicians, weren't able to prove it. He most likely didn't have a simple proof, right? It's a simple statement, and now that it's been proven, it's a simple thing to say that's true, but it was very difficult to show it. And it took, when we look at this, it took centuries of new mathematics until it actually was a small part of a larger piece of thing that was proven. And so it would be like a corollary. So this big thing was stated to be true, and Fermat's last theorem is inside of it, which makes a corollary of the big theorem. And so it was true. And it took, mathematics developed within the last couple of decades to even, nonstop, development of mathematics for centuries until this statement was actually shown to be true, and it's a true thing of a larger, more complicated area of mathematics. But that excitement of like, well, this is so simple, and let's give it a shot, and develops all of these new forms of mathematics and tools and processes to try and hit this conjecture. And there's lots of very wonderful statements that you can look at. If you're interested in it, you can go online and look for go ahead and research the Millennium Problems, which were 7 problems that were considered, these are fundamental. If you could show these, you would fundamentally change mathematics. And it's published in the year 2000. We have these 7 problems. And they said, it's Clay Mathematics Institute, and they said that, if you prove one of these problems, we'll give you $1 million. And just flat out, if you can prove one of these problems, it's worth to human civilization probably by far more than $1 million. And in terms of what mathematics does, is it completely changes, applied everything outside of us. These are the tools that are used within sciences. For example, one of my favorite quotes is from a physics professor I had, which was, all of science without mathematics is cheap talk, right? And going through these 7 problems, one of which has already been proven, and you can go and research this. These are things that are, point out this large roadmap in front of us, and mathematicians are building up slowly, maybe in the next century, maybe in the next 500 years, maybe in the next 1,000 years. We'll build this out to actually make sure all of these are solved, or, deal with them in a more unique way. And that process of constantly making these new statements that are true and new tools that are used within sciences, because these things model things that are, is an amazing process. And that's the nice thing about open problems. Some of them are very simple to state, like Fermat's last theorem, and some of them are much more difficult to state, like the Millennium Problems. But they build out, things that are of interest, and build out the tools of math. And that's what the techniques of proofs are, is to go through that building process. The proofs is this statement of building out and saying, this is what I got, where can I go?